So our first topic for this year is polar coordinates. We're just going to spend today and probably a little bit of tomorrow learning the basics of polar coordinates. And then when we get into derivatives and a little bit with limits, we're going to talk about polar coordinates. So the polar coordinate system is just like the rectangular coordinate system, and it's in that it's a way that you can graph different equations. But the polar coordinate system is really good for graphing things that are, circular, things that are cyclical, we'll say, things that repeat over and over again. So things that include like sines and cosines of angles in them are really easily graphed in the polar coordinate system. The polar coordinate system consists of a polar axis. The polar axis extends from what we normally call the origin in the rectangular system, or we call the pole in the polar coordinate system, off to the right. It's just a ray that has that pole as the endpoint and extends infinitely to the right. And the way that we label points in the polar coordinate system is r, theta, where r is the distance from the pole to the point, and theta is the angle that goes from the polar axis counterclockwise around. So this point looks like it could be whatever r is, 5, maybe pi over 6, or maybe pi over 4, something like that. They can be written using degrees or radians, doesn't matter. Generally, we're going to write them all with radians, but it could also be written using degrees. And counterclockwise gives us positive angles, and if we choose to go clockwise, then that would give us negative angles. And the r values can also be positive or negative. They can also be 0. So no matter what the angle is, if r is 0, the point is located at the pole. That's going to be an important point that we're going to deal with later on. But a positive r value goes out at that exact angle, and a negative r value goes the opposite way. So suppose theta was, we'll just call this pi over 4. The point 2 pi over 4 might be out here, but the point negative 2 pi over 4 would extend the opposite direction out. Everybody good with that so far?
Yep.
Yes.
Spectacular. Look at that. You guys did a good job. You unmuted yourself and let me know. Oh, and somebody has typed in the chat, which sometimes open, which is a yes. All right. Off to a good start. So first thing we're going to do is we're just going to graph a few points and make sure we can graph points. So this is why I gave you some polar graph paper in case you needed it. If I'm looking for the point 2, 2 pi over 3, all I got to do is find the angle 2 pi over 3 on my polar graph paper and go out 2 units. Look at that. It's 2, 2 pi over 3. Very exciting. Is there another way that I could label that same point? The answer is yes. You're supposed to unmute yourself and say yes.
Yes.
Good work. Nice job. And how else could we label that point 2, 2 pi over 3?
You can go in the other direction.
What do you mean the other direction?
I think you can use a different angle, right?
Yep. So what angle do you want to use? It's got to be the one coming out exactly opposite of it, right? Which would be 5 pi over 3. And so we could say 5 pi over 3 would be the angle, but then instead of an r value of 2, which would come this way, we'd have to use an r value of negative 2. Those are equivalent points. Those are the exact same point. Negative 2, 5 pi over 3, and 2, 2 pi over 3. We could have also gotten a different angle here. We could have said that this was the angle negative 4 pi over 3. So we could have said 2, but negative 4 pi over 3. Or instead of calling it 5 pi over 3, that could have been negative pi over 3. And then we'd have the point negative 2, negative pi over 3. Good or not? Yeah.
Yes.
No, yeah. So the difference here is that if the rectangular coordinate system, there's only really one way to label any point, but in the polar coordinate system, there are an infinite number of ways to label each point. Right? What about this one? Negative 4 pi over 3. So pi over 3, and we're going to go to negative 4. So rather than coming straight out at pi over 3, we're going to go the opposite direction, out 4 units to negative 4 pi over 3. Everybody good with that? Okay. And so we could also have said that the angle is 4 pi over 3, and it has an R value of 4. So we could have 4 comma 4 pi over 3. That'd be good. Or any number of other points that we could make. I mean, I could go around here, 5 times, let's say, to 10 pi, and then go another 4 pi over 3 and call it 4 comma 10 pi plus 4 pi over 3. It's 34 pi over 3. Right? We can do that if we wanted to. Good or no?
Good.
Yes. Perfect. So this is the way you can get different representations. R theta is always equal to R comma theta plus 2 pi. Or really theta plus 2 pi times n, where n is any integer. So you can always add 2 pi or 4 pi or 6 pi or 8 pi to that angle and get the same value. You can also subtract 2 pi, 4 pi, 6 pi, 8 pi to get the same point. And then you can also take the opposite of the R value and add pi plus any integer, or pi times any integer to the angle. And that's what we did on a couple of those, just to take a look at them. Okay, so that's a general formula to find a different representation of the point. You won't have to do that very often, just sometimes it might be nice to have, if I gave you the point 2 comma 7 pi over 3, it might be nice to know that's the same as 2 comma pi over 3 to make life a little easier. Okay, so there is obviously going to be a relationship between polar coordinates and rectangular coordinates and a way to convert back and forth between the two. So it's pretty important that we know how to do that. So what I've done here is I've drawn an xy coordinate axis here, and we've plotted some point P, which is the point x comma y. Right? We've gone over x and we've gone up y. Well, I've also turned these little legs here into a right triangle with an angle theta and an R value as the hypotenuse of that right triangle, where this is a right triangle, obviously, because that's the point xy, where we've gone up y units. Everybody good with the picture? Sort of like overlapping a rectangular coordinate system with a polar grid and calling the point R theta the same as the point xy. Good or no?
Great.
Perfect. Okay, so what's the cosine of theta according to this picture?
X
Over
R.
R. And what's the sine of theta? Just using our right triangle trig, right? Sine of theta ought to be y over r.
Yes.
So what does that tell you about the conversion between polar and rectangular? What does x equal? X ought to equal r cosine theta, and y ought to equal r sine theta. Good or no?
Splendid.
Wonderful. All right. And what about x squared plus y squared? What should x squared plus y squared equal according to the Pythagorean theorem?
R.
Yep, should be r squared, that hypotenuse r squared. And what about the tangent of theta?
Y over X.
Y over x, right? Tangent of theta should be y over x. So that should be pretty straightforward to convert back and forth. We're just going to use those 4 formulas. The first two, x equals r cosine theta and y equals r cosine theta. These are going to help us get from polar to rectangular. And then the other two will more generally be used to take us from rectangular to polar. So you will want to know those 4 things, those 4 formulas. X equals r cosine, y equals r sine, x squared plus y squared is r squared, and tangent theta is y over x. So make sure you memorize those ones. Everybody good so far? Okay, so let's convert a couple of points from polar into rectangular coordinates. So we got the point 2, 3 pi over 2. How are we going to convert that into rectangular? What's the first formula we're going to use? So we're going from polar to rectangular. So which one should we be using?
X equals r cosine theta.
Great. So if x is r cosine theta, all we got to do is say x is equal to r times the cosine of 3 pi over 2. And what's the cosine of 3 pi over 2?
0.
It'd be 0, so 2 times 0 is 0. And what about our y value? Y ought to be 2 times the sine of 3 pi over 2. And what's the sine of 3 pi over 2?
-1.
Okay, so that gives us -2 here. And so we've converted 0, -2. Easy enough? Great. All right, what about the other one? X should be -8 cosine pi over 3. And y ought to be -8 sine of pi over 3. Yeah? What's the cosine of pi over 3?
½
So -8 times a half gives us -4. And sine of pi over 3 is √3 over 2. So we get -4 √3. So our coordinates ought to be -4, -4 √3. Easy enough? Great. Okay. If we want to go the other direction, so if we want to convert a point from rectangular to polar coordinates, there's a little bit more to it. We're going to use the other two formulas, but the first thing we need to always do is we need to determine the quadrant that the point xy is in first. That way we can get the appropriate angle that's in that same quadrant when we do this last step. So let's see if we can go through and do a couple of these. Should be, I hope, pretty straightforward. So we want to convert the point -1 √3 from rectangular into polar. First thing we want to do is figure out which quadrant the point -1 √3 is in. Well, what quadrant is -1 √3 in? Should be in the, which quadrant?
Second.
Second quadrant, right? This is in the second quadrant, -1 √3. Okay. And so then we will just use r squared equals x squared plus y squared to get that r squared is -1 squared plus √3 squared. What's -1 squared plus √3 squared? That should be 4. So what does r equal? R is
2.
2. And then we'll use tangent theta equals y over x. So tangent theta is -√3. So in the second quadrant for tangent, what angle comes out to have a tangent of -√3?
2 pi over 3.
Yeah, it should be 2 pi over 3. So this just becomes the point 4, 2 pi over 3. Everybody good with that?
Wait, wouldn't it be 2?
Oh, sorry, 2 pi over 3. Yeah, I just looked at the 4 I had written up there. My fault. I know we wrote r equals 2, and then I decided to just ignore that. Yeah, 2, 2 pi over 3. Good? Great. All right. why don't you guys try and do this one really quickly on your own? We'll do this from time to time where I make you do it on your own and then we'll go over it. You guys all finished with that or no? Way to respond. What does r squared equal? It's -2 squared plus 2 squared, which is 8. So what does r equal? 2 root 2? Is that what you all got?
Yes.
All right, and then tangent theta was y over x, or -1. And what quadrant were we looking at here? -2, 2. Second quadrant again, huh? All right, so we're looking for the second quadrant angle where tangent is equal to -1. What's that theta value?
3 pi over 4.
3 pi over 4. So our point should be 2 root 2, comma 3 pi over 4. Good or no?
Good.
All right. We should also then be able to turn a polar equation or rectangular equation into the other one. So first, we're going to convert x plus y equals 5 into a polar equation. And whenever we write a polar equation, if possible, it won't always be possible, but when possible, we want it to be in the form r equals something, all in terms of theta. So it's a function of theta. So how are we going to convert x plus y equals 5 into a polar equation? Got to get everything in terms of r and theta. So how do I get x in terms of r and theta?
Substitute r cosine theta.
Yep. So we'll have r cosine theta plus, what are we going to substitute for the y? Ought to be r sine theta equals 5. And how do I solve that for r?
Factor like r and then parentheses cosine theta plus sine theta equals 5.
Wonderful. And then divide, right? Easy enough. And that should turn out, if we graph that, which we're going to do right now on Desmos. Desmos will be your best friend for a long time here. If we take r equals, what was it, 5, right? Divided by cosine theta plus sine theta. And it just comes out to be this linear equation, which, I mean, x plus y equals 5. I think we should know that that would be the same as y equals -x plus 5, right? And that's exactly the linear equation that we end up with there. So you can graph these in Desmos. And in fact, in Desmos, if you want, you can go into the settings and you can turn it into a polar grid also, similar to what we had before. So if you want to look at it on a polar grid, you can. It gives you the r values and it gives you the theta values as well. That'll be more useful when we're looking at the things we normally graph on polar grids. Everybody good there? I did share the Desmos, right? You guys can all see Desmos.
Yes.
Yes.
All right. And if you don't have the Desmos app on your phone, I would suggest downloading the Desmos app on your phone. It's super convenient to have. All right. Let's do another one. 3x minus y equals 6. You should be able to do that one really quickly. All we're going to do is replace the x's with r cosine theta and the y's with r sine theta. So we're going to have 3r cosine theta minus r sine theta equals 6. Factor out the r's, and you got 6 over 3 cosine theta minus sine theta. And I won't bother to graph that one on Desmos, but hopefully we got the idea there. Good or no?
Good.
Cool. All right, what about this? R equals 3. What do you guys think that should look like?
A circle with radius 3, perhaps.
Should be a circle with a radius of 3. It's a lot simpler than writing out the equation in rectangular coordinates of a circle centered at the origin with a radius of 3, right? What is a circle centered at the origin with a radius of 3 in rectangular coordinates?
X squared plus y squared equals 9.
Yeah, exactly, right? Which we could get from here. I mean, just square both sides of this. R squared equals 9, right? And what does R squared equal? R squared is x squared plus y squared. But if we were to go into Desmos and take a look at it, we'd see that putting in just R equals 3 is literally that. It's a circle centered at the origin with a radius of 3. And we can look at it on the polar grid if we want. It's got the radius of 3 centered at the origin. Good or no?
Good.
All right. Okay. So you'll want to know that anytime you just see R equals a number, that is always just a circle in polar coordinates. It's a circle with that radius, and it's centered at the origin. Cool. What about this? If it's just an angle, we won't be able to grab this one in Desmos, but what is theta equals pi over 4? What do you think that's going to look like?
A line along that angle.
Yeah, it should just be a line along that angle, and it should extend not just along pi over 4, but also coming out the opposite side of pi over 4. So for any positive or negative r value. And we should be able to figure out what that equation is in rectangular coordinates. What do you think we would do to do that?
Take the tangent of both sides.
Yeah, if we take the tangent of both sides, tangent of theta is supposed to equal what? Should be y over x. And what's the tangent of pi over 4?
1.
1. So we just end up with y equals x. And I think we should know that that's for sure just a line across theta equals pi over 4. But we'll graph it on here and see that. There's y equals x. Right there between pi over 6 and pi over 3 is pi over 4. And it's extending in both directions infinitely. Good or no?
Good.
Wonderful. Should be a pretty easy day so far today, and in general, all day today. Do one more of these before we get into the ones that are really going to matter a lot. So we're going to R equals secant theta. What do you want to do with that one?
R equals root x squared plus y squared. Right, and then
That sounds complicated.
yeah.
That sounds worse than I want it to be. Do we have anything with a secant in it in any of those equations?
Can't you square both sides or something? I don't know.
You just do r cosine theta equals 1.
I could do that. Let's do that. That sounds like the best option. We could call this r equals 1 over cosine theta, couldn't we? And then just turn that into r cosine theta equals 1. And what's r cosine theta? It's x. Squaring both sides of it, I don't know, somebody mentioned that. I don't know, I'd have to think about that. X squared plus y squared equals 1 plus 1 squared. Yeah, you could do that. You could square both sides of it, and it would come out to work as well, I think, just for fun. Why not? We could do that. If we squared both sides of it, we'd have this, right? And r squared is x squared plus y squared. What's secant squared equal to? It's not equal to anything in rectangular coordinates yet, but how can I rewrite secant squared theta using a Pythagorean trig identity?
Could it possibly be tangent squared plus 1?
It better be that. Tangent squared theta plus 1 or 1 plus tangent squared theta. And what's tangent squared theta? That'd be y squared over x squared, right? Let's see if that's gonna, thought that was gonna work out. Maybe that's not gonna work out. So no, that'll work out just fine. Maybe. Maybe not. Yeah. Is that gonna simplify down? Maybe that won't simplify down so nicely. In my head, I thought it would. What does that become? X to the 4th plus x squared y squared equals y squared plus x squared. Yeah, that's not going to work out real nicely. Maybe we shouldn't have tried to do that. Do it the easy way. There's probably a way to deal with that, but I don't want to worry about it now because we're on a time crunch here for the next 9 weeks. So this is the nice, easy way to do it. And what does that look like? What's x equals 1 look like? Just to remind ourselves, what does x equals 1? Should just be a straight vertical line. Yeah. Or if I went back and typed in r equals secant theta, should be that same thing, right? Just that straight vertical line. Oh, I didn't show it on Desmos. There it is on Desmos. R equals secant theta. All right. We already graphed these. We already looked at the graphs of these, so we're going to ignore that for now. Let's take a look at this one. R equals 4 cosine theta. Any idea what that one's going to look like? All right, let's see if we can turn it into rectangular coordinates then and see if we can figure out what it looks like. If we have r equals 4 cosine theta, any thoughts on how we're going to turn that into rectangular coordinates? And we'll go back and try and graph it once we've done that. Any ideas on how to do that?
Can you turn the cosine x into, or the cosine theta into an x, and then it would be, if you like square it, so it would become r squared equals 4r cosine theta, which would become 4x.
Great. R squared equals 4r cosine theta, just multiplying both sides by r to start, right? And
yeah, so then it become x.
Yep, 4x on the right-hand side. And then what about on the left-hand side? It should be x squared plus y squared equals 4x. What is that an equation of?
An ellipse, right?
No, close enough.
Circle.
It's a circle. It's just a circle that's not centered at the origin.
Okay.
So we could put that into standard form if we wanted to by subtracting the 4x, and then we would have to do what? We'd have to complete the square. Everybody remember doing that sometime in their life? Half of -4 is -2, squared is 4, so add a 4 to both sides. And it becomes x minus 2 squared plus y squared equals 4. So it ends up being a circle that's centered at what point? Should have a center at 2, 0, and it should have a radius of 2. Yeah? Everybody familiar with that from years past? So if I try to graph r equals 4 cosine theta, that's exactly what we get. We get a circle centered at the point 2, 0 with a radius of 2. Everybody see that? All right. Have some of you been like typing in the chat? Oh, some of you have been typing in the chat. It hasn't been notifying me of that this whole time. That's weird. Normally it notifies me when people type in the chat. Oh well. I'll try to keep an eye on that. So I'm going to just sketch the graph on here. Look at that circle. That was awful. That's better. So there's our circle. Any thoughts on what our next one for sine theta is going to look like?
The same thing except the origin is at 0, 2.
Yeah, we're gonna have our center, right?
The center, that's what I meant.
It's gonna look just like this. It's gonna be a circle still with a radius of 2 centered at the point 0, 2. And we could definitely, I mean, I'm not gonna go through and we could do this r squared equals 4r sine theta to give us the x squared plus y squared equals 4y, but I think we could see that that's going to turn into that same exact thing. And the radius was equal to the square root of this value, right? So I'm going to open up Desmos real quick here. And we're going to talk a little bit about how these values affect our graphs. So there's r equals 4 sine theta. What do you think would happen if I changed the 4 to a 9?
The radius would increase.
Yeah, we should just end up with a radius of, we should end up with a radius of, looks like what? 4.5, right? Suppose this was 2. Well, we'd end up with a radius of 1. If this was 6, we'd end up with a radius of 3. Right, so we're just going to have a radius that's half of whatever this value is. And that comes from the completing the square of it when we were to go through and convert it into rectangular. And anytime I switch this over to cosine, it's going to drop that circle over here into the first and fourth quadrants. And what do we know about cosine in the first and fourth quadrants?
It's positive.
It's positive, right? And note that when we had sine, it was in the first and second quadrants. Those are the quadrants that sine is positive in. Everybody good with that? That the circle sits in the 2 quadrants in which sine is positive if it's a sine circle, and it sits in the 2 quadrants in which cosine is positive if it's a circle made with cosine. Good or no?
Good.
Good.
What do you think would happen if I threw a negative sign at the front of this?
It'd be in the other quadrant. So for sine, it'd be, yeah, there.
Yep, it would drop down there exactly into the quadrants in which sine is negative, quadrants 2 and 3. Doesn't matter what my coefficient is. It's negative, right? Put in some whatever values I want here. Make this circle as big as I want, but if there's a negative in front of it and it's sine, we're going to end up with that circle in the quadrants in which sine is negative. And if I have a negative cosine, we will note that it will be in the quadrants in which cosine is negative. Everybody good there? That should make it really easy for you to graph circles in polar coordinates. It's way easier than having to deal with it in rectangular, which makes sense because polar grid is circular. So it should be easy to have an equation of a circle rather than in a rectangular coordinate where the grid is square. It's going to be a little more difficult to get there. Any questions or issues with that? Okay, so it's a very important point that the positive cosine values give you this in the positive cosine quadrants. The positive sine values put it in 1 and 2, the quadrants where sine is positive. And if you throw a negative, it puts it in the quadrants where that trig function is negative. This is a pattern that's going to repeat itself over and over and over and over again with basically every function that we deal with in polar coordinates. So it's an important concept. Everybody feeling all right? Everybody feeling good? Okay. So this is just the basic idea behind it. If it's a cosine, you got your diameter of A and it's in 1 and 4. If it's a sine, you got a diameter of A and it's in 1 and 2. Okay. So if I said R equals 3 sine theta, that should be a circle with a diameter of 3, radius of 1.5, up in quadrants 1 and 2. If I said 2 cosine theta, that should be diameter 2 down here, quadrants 1 and 4. And if I said negative 5 cosine theta, should be over here like that. Everybody good there?
All good.
All right, spectacular. So we will actually stop there just a little bit early today because that's going to transition us to something brand new that's going to become a little bit more difficult. And there's a lot to do with it, and it's going to take way more than the 5 minutes we have left. So I think that will be good for today.